Okay, so when an earthquake hits, we're not just talking about a building shaking. We're talking about a potential catastrophe, especially when that building is a massive industrial plant. Today, we are going to demystify the standard that keeps them standing. IS 1893 Part 4. Let's jump right in.
For any engineer or project manager out there, this is not some theoretical problem. The decisions you make have real-world consequences. They impact the safety of everyone on site, they protect assets worth billions, and they can prevent huge environmental disasters. The stakes could not be higher. And this standard? Well, this is your roadmap to getting it right.
Now, before we really dive into the nitty-gritty, if you find this kind of breakdown helpful, do me a favor and hit that subscribe button. We're always putting out explainers on IS standards to help you stay sharp and up to date. So, what's the big idea behind this whole standard? Well, it's not just about making sure a building doesn't fall down. That's kind of the bare minimum. This standard is built on a much smarter, performance-based approach. It asks a better question. How should a structure actually behave when it's under different levels of seismic stress? And this, right here, this comes straight from Clause 6.1.3, and it lays out the three-tiered safety philosophy perfectly. First, for a minor, frequent quake, the goal is simple: zero damage. Then, for a moderate event, what the code calls the Design Basis Earthquake, or DBE. Look, some non-structural damage is okay as long as the plant can stay operational. But for that rare, major event, the Maximum Considered Earthquake, or MCE, the #1 absolute priority is preventing collapse. It's all about life safety. This idea is the bedrock for everything else we're going to talk about.
Okay, so how do you actually apply this philosophy? Well, the very first thing you have to do before you even think about a calculation is categorize your structure. And let me tell you, this is not just some box-ticking exercise. This is, hands down, the most critical decision you will make in the entire design process. So, Clause 7.1 breaks it down into 4 categories, and here's the key thing to get. It's all about the consequence of failure. Category 1 is for structures where a failure would be an absolute disaster for the public. Think a tank holding toxic chemicals. Category 2 is for things that could cause a major fire or explosion inside the plant, like a critical pipeline. Category 3 covers structures that are really expensive to replace but not necessarily hazardous, like a main turbine building. And then Category 4 is basically for everything else, like an admin office on site.
And this chart just shows you exactly why that decision matters so much. Based on Table 2, your structure's category gives it an importance factor, which we call I. And you can see it right there. A Category 1 structure has an importance factor of 2.0, while a standard Category 4 structure is just 1.0. What does that mean? It means the Category 1 structure has to be designed for twice the seismic force. It's a direct mathematical consequence of how much risk it carries.
All right, so let's get into the core calculation and see how this all fits together. Now that we get the philosophy and we've categorized our structure, we can look at the real engine room of the standard, the formula that actually determines the seismic force. And here it is, the Design Horizontal Seismic Coefficient, or Ah. This little formula from Clause 8.32 is what turns all those principles we just talked about into a single concrete number. You take this coefficient, you multiply it by the building's weight, and boom, that gives you the total horizontal seismic force, the base shear, that your design has to be able to handle. So let's unpack this really quick. Z is your zone factor. Simple enough. Are you in a high-risk area or a low-risk one? I is that importance factor we just hammered home. How critical is the structure? Now R, the response reduction factor, this is where things get really cool. This is basically your reward for smart design. If you use ductile systems that can bend and absorb energy instead of just snapping, the code lets you design for a lower force. And finally, S/G is the spectral acceleration. That takes into account the local soil and how your specific building is likely to vibrate. See, every single part of this equation is a thoughtful input based on real-world conditions.
So once you have that design force, the next question is, what do you do with it? How do you analyze it? Well, the standard doesn't just give you one option. It's not a one-size-fits-all kind of thing. It actually provides different tools for the job depending on the risk level. Clause 10.1 basically gives us a decision tree.
If you're working on a high-risk Category 1 structure, a detailed dynamic analysis is mandatory, no way around it. Same goes for Category 2 and 3 structures if they're in high seismic zones. But for lower-risk stuff, like a Category 4 building or even a Category 2 in a low seismic zone, a simpler, more straightforward analysis is totally fine. The key takeaway here is that the amount of engineering effort you have to put in is directly proportional to the risk involved.
All right, let's just zoom out for a second and look at the big picture. If there's one thing you take away from all this, what should it be? It really boils down to this. IS 189 Part 4 is not just some rigid cookbook of rules you have to follow blindly. It's a modern, smart, risk-based framework. It makes you think first about the consequences of failure, and then it scales everything, from the importance factor to the type of analysis you do, to match that level of risk. The entire point is to build real, actual seismic resilience.
So I'm going to leave you with this one question to think about for your own projects. When you're applying this standard, you're answering a fundamental challenge. Are you designing a structure that's just built to stand, or are you engineering something that's truly built to survive and do its job when it matters the most?
I really hope this breakdown of IS 1893 Part 4 has helped clear things up. If you found it valuable, please go ahead and like, share, and subscribe to ISO Automation Lab. We've got plenty more deep dives into critical standards coming your way. I'll see you in the next one.